All right, here we go. 3.2, conditional probability. All right, I want to preface this by this is one of the more difficult sections, at least in terms of the concept to understand. So pay close attention, rewind as needed. Let me know what questions you have in class when you see me. So conditional probability. Basically what this is, it's the probability of that some event has happened, so probability of some event A, given that another event B has already occurred. Okay, so probability of A given that B has occurred is what conditional probability is. So in other words, so we know B has happened. Okay, so event B has already occurred. We know it's happened. Now that that has happened, what's the probability that A occurs? Okay, so something to help you in this section. Okay, so you'll be given something has happened. So for whatever you're given, restrict your vision to just that. Okay, that's your denominator. Now this is going to make more sense when you see an example. But restrict your vision to the given. That gives you your denominator. Then out of what you see there, out of what you're given, how often does the other event occur? Okay. So let's take a look. Actually, before an example, let's get to talk about this. This is the formula for conditional probability. I don't necessarily advise using this all the time because I think it makes it more complicated than it is. But it's important to know what it is because there's a couple of times where you're going to need to use it. So say A and B are just two events in a sample space, some experiment. Probability of B is not equal to 0. In other words, B has to occur. Okay. So conditional probability of, so if we say A given B, we write it like this. So that vertical line means given. Okay. So that means given. So A given B. So A given B, what that is, it's the probability of both A and B happening divided by the probability of B happening. So you know I said before, so we restrict your vision to B, whoever you're given. So that's our denominator, B. All right. The numerator is out of B. What's the probability of our event? A. That would be the intersection of A and B. Okay. Kind of think about a Venn diagram. All right, but anyways, that's a formula. We use that sometimes, but not always. It's a lot of times easier not to necessarily use the formula. So, example here. We've got our good old urn that everybody loves, containing 3 different color balls. They all are marked with something with a different number. So reds are marked as 1, 2, and 3. Blue is marked 4. White is marked 5, 6, 7, and 8. We take one out at random and we know the color. So first off, what's the probability that it's red? Nothing complicated here. There's 8 of them, 8 balls, 3 are red. So 3 out of 8, right? Okay. In the second one, it says if the ball is known to have an even number. So that is my given. We want to know what's the probability that it's red. So how we write this with notation, we'd say it's the probability of red given it's an even number. So this is where it's easier to not worry too much about that formula and just think, restrict our vision to what we're given. So restrict our vision to the even numbers. So in other words, let's just get rid of all these odds. We don't care about them right now. So I've got these even numbers now. So restrict our vision to the evens, to my given, that's my denominator. How many evens do we have? So I have 1, 2, 3, 4 even numbers. Okay, given, even, that's our denominator. Out of those evens, how many are red? Well, let's go find it. Out of those evens, there's one of them that's red, so probability is 1/4. So if it's known to be even, probability that it is a red is 1 out of 4. Okay, so there's 4 known evens, one of those is red. So that's where, using the formula, I think, kind of overcomplicates it and just kind of think logically about it. Again, as you're doing these, your denominator is always whatever the given is, whatever's after the line. Okay, different example. So we've got Director of State Tourism is doing a survey of summer vacation plans of people going through Indianapolis Airport. So the data collected yield the probabilities shown below. So we've got people that plan to visit the state this summer and drive by personal car, or drive their personal car. People that plan to visit the state and use commercial transportation, and people that do not plan to visit the state this summer. Fortunately, it's a lot, shockingly. So next slide has the question. So suppose that a survey clerk selects a survey at random. So we just pull out a random survey and notices the tourist plans, or does not, notices that the tourist does plan to visit the state. Okay, so what this is saying is we're given, so I'm holding up this survey that says they're visiting the state. So given they plan to visit. And then it asks, what is the probability that the person plans to use commercial transportation? So given plan to visit, what's the probability of commercial transportation? So again, don't mess with the formula here. So we're given that they plan to visit. So we restrict our vision, that's our denominator, to plan to visit. So I don't care about this group down here. They're meaningless to me right now. Okay, they don't like Indiana, so forget about them. So given the plan to visit, that's these. So that's my denominator, those two combined. 0.12 plus 0.18, 0.3. Okay? So out of the people that plan to visit, how many are doing it and using commercial transportation? Well, that's this second one here, right? So 0.18. And there's my answer. 0.18 out of 0.3. Simple as that. Just reading very carefully, noting that what it tells us right up here is given that. So we're given that they're planning to visit, and then probably out of those, probably that they're using. Right. The other topic in this section is about independence. Right, and this is something that kind of trips people up sometimes. So first off, what independence is, this is independence is events A and B are said to be independent if, marker, here we go. So they're independent if the intersection of A and B is the same as if I take A times B. All right? So they're independent if that happens. So really, it's the only way that we can actually prove independence. So you'll be asked sometimes to decide, are these two events independent? Okay? This is what you'll use. You also might be given, you're told that things are independent. All right, if it says somewhere in a problem that two events are independent, that's basically telling you that you're going to use this somehow. But basically what independence is, right here, okay, if probability of A occurring is not affected by B occurring, we say A and B are independent, or vice versa. Okay, if B occurring, probability of B occurring is not affected by A occurring, they're independent. Okay. One thing to know, this is very important, people mix this up all the time, right? Independence is not the same as being disjoint. They sound similar, like they mean similar things, but they do not. Okay, disjoint means they have nothing in common. If one occurs, the other can't occur. Well, independence means knowing B occurred doesn't affect the probability that A occurred. But basically, they have to both occur for independence. So that means they can't be disjoint. Okay? So if they're independent, they cannot be disjoint. Or if they're disjoint, they can't be independent. Okay, so if A and B are independent, kind of something that comes from that. So we could kind of use our formula for A given B. All right, so A given B is this formula here, right? A intersect B over B. If we're told two events are independent, that means this right up here. A intersect B is just A times B, so A intersect B is A times B. So if we look at that, what happens to the B's? Those cancel, right? This multiplication. So notice what we end up with. So if they're independent, then the probability of A given B is just the same as probability of A. Again, if they're independent. So if we know they're independent, A given B is just A. If you think about why that is, back up here, probability of A occurring is not affected by B occurring, so that means given B doesn't affect A. So it's still just the probability of A. Right? Same thing works. This formula looks identical, pretty much, just flipped around. If we had B given A, if they're independent, that's just probability of B. Okay. Again, note that's if they're independent. So look at an example now. All right, so back to the urn, same situation, same numbers, everything. So find these probabilities first. So the first probability that a red ball is drawn, we already did that. That was 3 out of 8. Okay, the second one, probability that an even number is drawn. So I have 1, 2, 3, 4 evens out of 8. So 4 out of 8. Probability a white ball is drawn. So I have 4 white balls, so 4 out of 8. So now we want to decide, are A and B independent, and then are B and C independent? So now we're going to use our formula here. So A and B, so that's red ball and even. So are red and even independent? So basically what that means is, does red intersect even? Is that equal to the probability of red times the probability of even? Okay? We test that out. If it's equal, they're independent. If it's not equal, they're not independent. So red intersect even. So what that means is the probability of drawing a red even ball. So a ball is red and even. So how many red even balls are there? So here's the reds. Out of those that are even, there's 1. It's the number 2. So there's 1 red even. So the probability of being red and even, if we're drawing from all of the balls, will be 1/8. Okay, we want to check, is that the same as the overall probability of red times the overall probability of even? Which we've already done those two. Overall of red is 3/8. Overall even is 4/8. 3/8 times 4/8 would be 12 out of 64. That reduces to what? 3 out of 16, which you can see not equal 1/8. So those are not independent. Okay. So now checking, are B and C independent? Probably guess what the answer is going to be here, but we'll go ahead and show what it is. So B and C are independent. We need to see if the probability of even intersect white, is that the same as probability of even times probability of white? So probability of drawing an even white ball. So there's 2 of those, right? 2 even whites. So 2 out of 8. There's 8 to choose from total. Probability, again, we're checking this. We haven't shown it yet. Probability of even, we already found, is 4 out of 8. Probability of white was 4 out of 8. Okay, 4/8 times 4/8, that's just a half times a half, which is 1/4, right? Or you can multiply it out and do 16 over 64 and reduce it, but that's 1/4. That's the same as 2/8. So no question anymore, they are equal. So these are independent events. Okay, so an even number and a white one, those are independent, because knowing it's even doesn't change the probability of it being white, or knowing it's white doesn't change the probability of it being even. That is checking for independence. That is it. Yep. So that's section 3.2. Let me know questions in class. We can do a few more examples in class if you guys would like.